Hello everyone. In this video, we discuss an important method to solve second order linear differential equation with variable coefficient. The method is known as variation of parameter. So let's see how we perform this method. Let the given equation is d2y by dx2 plus p dy by dx plus qy equal to r, which is a second order linear differential equation with variable coefficient in its standard form, that is the coefficient of d2y by dx2 must be 1. Now in order to solve this equation by method of variation of parameter, we consider the homogeneous part of this equations. See, in a differential equations, the part which consists of dependent variable and its different derivative is called homogeneous part of the differential equations, and the other part which is function of dependent variable x is known as non-homogeneous part of the differential equations. So to solve equation first by method of variation of parameter, we consider the homogeneous part of this equations. And what is the homogeneous part of this equation? Equating the right hand side to 0, that is put the non-homogeneous part 0, we get the homogeneous part of this equation. First we have to obtain the solution of this equation, that is the solution of homogeneous part. Since it is a second order linear differential equation, so its solution consists two arbitrary constants C1 and C2. The most general form of solution of this equation is y equal to C1u plus C2v. Suppose this is the solution of homogeneous part. Now parallel to this solution, we consider the complete solution of equation first. And how we consider these arbitrary constants C1 and C2, we replace this constant by arbitrary function of x. So let the complete solution of equation first is y equal to au plus bv. The constant C1 and C2 in the solution of homogeneous part, we replace these constants by a and b, which are arbitrary function of x. So the complete solution of equation first is y equal to au plus bv, where a and b are arbitrary function of x. See, C1 and C2 are the constant, where a and b are the arbitrary function of x. These functions satisfying a condition. The condition is a1u plus b1v equal to 0. This is the condition the arbitrary function a and b satisfy, where a1 and b1 are derivative of a and b with respect to x. Since equation 4 is the complete solution of equation first, we have to identify the value of a and b, and putting these value of a and b in equation 4, we get the desired solution. Now as equation 4 is solution of equation first, therefore it must satisfy equation first. So putting the values of y, dy by dx and d2y by dx2 from 4 into first, equation first reduce in the form of, this is the form which equation first take after putting the values of y, dy by dx and d2y by dx2. The form is a1 u1 plus b1 v1 equal to r, where a1 and b1 are the derivative of a and b with respect to x, and u1 and v1 are derivative of u and v with respect to x. Now equation 5 and 6 are simultaneous equation in a1 and b1. So after simplifying equation 5 and 6, we get the value of a1 and b1. Integrating a1, we get the value of a, and integrating b1, we get the value of b. So putting these value of a and b in equation 4, we get the desired solution. So this is the process we use the method of variation of parameter. Let us take few examples on the method of variation of parameter. The question is, solve d2y by dx2 minus y equal to 2 upon 1 plus e raised to x by method of variation of parameter. So the given equation is d2y by dx2 minus y equal to 2 upon 1 plus e raised to x. Now in order to solve equation first by method of variation of parameter, we consider the homogeneous part of equation first, which is d2y by dx2 minus y equal to 0. This is the homogeneous part of given equation. First we have to obtain the solution of this homogeneous part, and clearly this is a linear differential equation with constant coefficient. So its solution is y equal to cf plus pi. But since the right hand side is 0, therefore pi is 0. Hence y equal to cf is the solution of homogeneous part. Now equation 2 can be written as d square minus 1y equal to 0. Now to find CF, the auxiliary equation is m square minus 1 equal to 0, and which gives the value of m as plus minus 1. That is, the roots of auxiliary equations are real and distinct, and hence the solution of equation 2 is y equal to cf, that is c1 e raised to x plus c2 e raised to minus x. So this is the solution of homogeneous part. Now we consider the complete solution of equation first parallel to this solution by replacing c1 and c2 with the arbitrary function of x, a and b. Let the complete solution of equation first is y equal to a e raised to x plus b e raised to minus x. C1 and C2 are replaced by a and b, where a and b are function of x, such that what is the condition a and b satisfy is a1 u1 plus b1 v1 equal to 0. This is the condition which the arbitrary function a and b satisfy. a1 u plus b1 v equal to 0. U is e raised to x and v is e raised to minus x. Now, since the equation 4 is the solution of equation first, therefore it must satisfy equation first. Therefore, putting the values of y dy by dx and d2y by dx2 from 4 into first, equation first reduce in the form of a1 u1 plus b1 v1 equal to r. a1 is the u1 is the derivative of u, that is e raised to x, and derivative of e raised to x is e raised to x, plus b1 v1 is derivative of v, that is derivative of e raised to minus x, and derivative of e raised to minus x is minus e raised to minus x equal to r. Now, equation 5 and 6 are simultaneous equations in a1 and b1. So, after solving this equation, we get the value of a1 and b1. Adding equation 5 and 6, b1 e raised to minus x and b1 e raised to minus x cancel. We get a1 equal to 1 upon e raised to x plus 1 plus e raised to x, and by subtracting equation 5 and 6 we get b1 is equal to minus e raised to x upon 1 plus e raised to x. So these are the values of a and b, a1 and b1. Now integrating a1, we get the value of a is minus e raised to minus x plus log 1 plus e raised to minus x plus c1, constant of integration. Similarly, integrating b1, we get the value of b minus log of 1 plus e raised to x plus c2. So these are the values of a and b. Putting these value of a and b in equation 4, which is the complete solution of equation first, we get the desired solution of equation first. Let's take another example. Solve d2y by dx2 plus 4y equal to 4 tan 2x by method of variation of parameter. The given equation is d2y by dx2 plus 4y equal to 4 tan 2x, which is a second order linear differential equation. Now, to solve equation first by method of variation of parameter, we consider the homogeneous part only, and the homogeneous part of equation first is d2y by dx2 plus 4y equal to 0. Equating the inhomogeneous part 4 tan 2x by 0, we get the homogeneous part of equation first. Now first we have to obtain the solution of equation 2, which is clearly linear differential equation with constant coefficient. So its solution is y equal to Cf plus Pi, but the right hand side is 0, therefore Pi is 0, and hence y equal to Cf is the solution of homogeneous part. Equation 2 also can be written as d square plus 4y equal to 0. Now, in order to find Cf, the auxiliary equation is m square plus 4 equal to 0, and which gives m equal to plus minus iota 2. Plus minus iota 2. And since the roots are complex, therefore the CF is roots are complex with alpha equal to 0 and beta equal to 2. So the CF is e raised to alpha x, that is e raised to 0x, which is 1, C1 cos beta x plus C2 sin beta x, beta is 2. So the solution of homogeneous part is y equal to C1 cos 2x plus C2 sin 2x. This is the solution of homogeneous part. Now parallel to this solution, we consider the complete solution of equation first by replacing C1 and C2 with a and b, the arbitrary function of x. So let the complete solution of equation first is y equal to a cos 2x plus b sin 2x. C1 replaced by a and C2 replaced by b. C1 and C2 are the constant, but a and b are the arbitrary function of x. So this is the complete solution of equation 4. We have to identify the value of a and b, and putting the value of a and b in equation 4, we get the desired solution. Now a and b are the arbitrary function of x satisfying a condition. And what is the condition? Condition is a1u plus b1v equal to 0. So a1u, u is your cos 2x, plus b1v, v is sin 2x. So the condition is a1u plus b1v equal to 0. Now since equation 4 is the solution of equation first, therefore equation 4 must satisfy equation first. So putting the value of y, dy by dx and d2y by dx2 from equation 4 into first, equation first reduce in the form of, and what is the format? Format is a1 u1 plus b1 v1 equal to r. So here a1 u1, u1 is derivative of u. So derivative of cos 2x is minus 2 sin 2x plus b1 v1. What is v1? Derivative of v. v is sin 2x. So derivative of sin 2x is 2 cos 2x is equal to r. So a1 u1 plus b1 v1 equal to r. Now simplifying this equation, we get minus a1 sin 2x plus b1 cos 2x plus 2 tan 2x. Now equation 5 and 6 are simultaneous equation in a1 and b1. So simplifying these equations, we get the value of a1 and b1. So to simplify equation 5 and 6, multiply equation 5 by sin 2x and 6 by cos 2x, and adding we get a1 cancel out, b1 sin square x plus b1 cos square x, b1 common, sin square cos square 1, here 0 plus 2 sin 2x upon cos 2x, multiply by cos 2x, cos 2x cancel. So we get b1 we get b1 equal to sine 2x, and similarly we get a1 is minus 2 multiplied by sec 2x minus cos 2x. Now integrating a1 and b1 we get the value of a and b. So integrating a1 we get a as minus whole multiplied by log sec 2x plus tan 2x, integration of sec 2x, and integration of cos 2x is sin 2x by 2, constant is eliminated, cancelled by 2, and the b is minus cos 2x by 2, 2 cancel, so b is minus cos 2x plus c2, constant of integration. Putting these value of a and b in equation 4, we get the desired solution. So this is how we apply the method of variation of parameter. In next lecture, we discuss few more examples in which homogeneous part is not constant coefficient but it is variable coefficient. Thank you.